My name is Kelsey Saunders, and I am the Building Science and Sustainability Coordinator at Sustainable.TO. And today I'm going to be presenting a research project that we began about 2 years ago, METHOD.TO, which is kind of a construction method as well as a wall assembly. So you'll see what I mean in a minute. And for those of you who don't know Sustainable.TO, we're a group of young and young at heart architects and designers with a passion for designing healthy, energy efficient, and affordable homes, which I think buildings really, and I think everybody in this room shares that passion as well. And so this is just a sampling of some of our projects, and this is our beautiful team here. And the one thing I love, about working in my office is that all of these designers are building scientists at heart. They're building science nerds at heart, so that makes my job really fun. So a few things first, just to discuss our process at Sustainable, is we're always first looking at passive design principles, and that's our starting point. So we're looking at orientation, insulation, and airtightness, and the floors, walls, and the roof. And as most of you who are designers know, that orientation in Toronto is challenging, especially with existing buildings. So we're focusing here today on insulation and airtightness and how we can optimize those. Our ethos at Sustainable is focusing on the trias energetica. So like I just said, reducing the overall demand first. And that has the least associated cost. That's essentially done with good design. Reusing nature's energy passively through passive design principles again. And then recycling renewable energy actively, and that has the highest associated cost. We want to reduce the amount of energy we need to generate. So as we've been trying to develop our most effective wall assembly, our ideal wall assembly at our office, we really like to use Rockwool. And we do that for several reasons. The health, so no off-gassing, it has good fire rating, it has fantastic hygrothermal performance, so drying to both sides, which is very important in our climate with heating and cooling. It has recycled content both in the manufacturing process and then afterwards can be recycled and returned to the earth. It's very durable, long-lasting, and it has great acoustic performance as well. So we try and use Rockwool when we can. And in developing our ideal wall assembly, we did a lot of research. We were trying to essentially see how much exterior Rockwool insulation we could use, specifically Rockwool, of course, because they're our local provider. So we were looking at, say, doing 3 inches of exterior insulation, and there's research for 3 inches. Building Science Corporation has done research, and then we wanted to do 6 inches of exterior insulation. We wanted higher R values and a lot of exterior insulation. And then we said, what about 9 inches? R36, that's a good wall assembly. We don't need any interior insulation, but there's no research done at this point 2 years ago for that. So we did our research into high exterior insulation wall assemblies, and what we were seeing is everything was done with foam. And we think this is because foam has a higher compressive strength, but there was no research done for 9 inches. So we thought, can we do it with Rockwool? So this is the persist method. It has exterior insulation and one membrane around the entire perimeter of the building. The remote method is very similar. The walls are fully exterior insulated, and the roof assembly is a traditional truss with batt infill. And just recently, actually, so this is after we began our research 2 years ago, they've developed a new assembly for the Eco Home, which is 8 inches of insulation, 4 inches, and then a course of horizontal strapping, and another 4 inches and a course of vertical strapping. So it's also an interesting assembly, and it's good to see that more people are kind of pushing the envelope with what we can do with Rockwool as an exterior insulating material. So our goals for this project, we had some high-level goals that we wanted to achieve, and we wanted a protected internal structure, so all of the insulation on the exterior. We wanted one continuous membrane that was going to control air, weather, and vapor. We wanted a continuous thermal blanket with minimal thermal bridging. And then we wanted a lightweight rain screen cladding just to protect this assembly from getting wet. And sorry, I'll just mention one more thing. We also one of our driving goals was to use materials that are readily available and that builders are comfortable with using already. Obviously, pushing more and more exterior insulation is a bit more, we had a bit of pushback from builders for that. But we're using materials that are familiar. That was important to us as well. So our hypothesis here was that we could use long screws and drill through the strapping, through the 9 inches, into the wood frame stud wall, and it would be structurally sound to support a lightweight cladding. From everything that we had seen in Building Science Corporation's data for deflection testing for lightweight claddings, we thought this would be okay. And I actually talked to John Straub, and he said, "Yeah, you're fine. Don't worry about it." So I trust that guy. I think we're okay. So, but we wanted to make sure, and our only way to do this, we thought, was to build a test shed, to build it ourselves with the help of local contractors to see how this was going to work. Our second hypothesis was that the effective R value of our wall assembly would be nearly the nominal R value. So this is just a comparison. A typical code minimum wall, everyone knows, is a 2x6 wall with a fiberglass bat or some kind of a bat. So that's about an R24. Your effective R value is less than R19. So you're losing a lot of R value through thermal bridging in the studs. With the Toronto method, with 9 inches of exterior insulation, you're getting an R36. And our hypothesis is that the effective R value would be R36, or at least around R36. Or if you have 6 inches, R24, almost around R24. So this is our preliminary sketch of this assembly. We wanted to make a complicated shape. Because we're architects, we wanted it to look cool. But also because we wanted to push the boundaries on, where is this assembly going to fail? If it's going to fail, we want to test it here. So we have this oddly shaped curved wall that you'll see in the actual construction images. So this is a peel away of our assembly. So first we have the 2x4 stud wall. Sorry, the writing's really small, but I'll just explain. 2x4 stud wall. We have a 1/2 inch OSB sheathing, and it's taped at all the seams with Sega tape. So that's our vapor control layer. It's a class 3 vapor retarder. We have blueskin VP, so it's a vapor open self-adhered membrane. That's our air barrier. And then also we have a peel and stick membrane around all the windows and at the roof, overlapping the wall. 9 inches of mineral wool, the Rockwool Comfort Board IS, and 1x3 vertical strapping, and then there's SIP screws, 12-inch SIP screws that's fastening the furring. And then we did a Shosugibon cladding, which is a burnt cedar, which is a cladding material that we really like using. It's very durable and just completely returns to the earth, so we really like that. And then also for our roofing material, we tend to go with corrugated Galvalume, just because it has a super long life, super durable material. So this is some images of construction. This is the OSB taped with Sega, so we taped it all seams. That's our vapor control layer. This is us. This is actually Mike Manning from Greenbuilt Homes who's here. And we also had Chris Henderson and Ryan Fields is here. I don't see, and Chris is right there, yeah, from Modus and Then. So those two contractors really helped us with how can we best build this? And they were on site with us a lot, giving us a lot of feedback and advice on how best to do this. And so this is us kind of installing the air barrier system in the water control layer. So this is it kind of sealed up, and you can see the curve on the wall there. It made the window openings very interesting to detail as well. And then we have these 12-inch screws. So you can see how long this is 9 inches of insulation. We have 12-inch SIP screws, which are quite challenging to source. And we had snapped a line for where the studs were, and we just kept layering it one by one. So actually you'll see that in the next image. We're layering, we did about 2 layers. We cut the top 3 inches off the insulation for the next layer, so we had 3-inch laps and seams for good air control, and also good thermal control. And then we would put in the first screw, keep adding insulation, put in the next one, keep adding insulation. So it helped us keep track of where the studs were, because that was one of the biggest pushbacks from contractors, was how are we gonna get those screws into the stud wall. And the same assembly on the roof. So this is our Shosugibon cladding, and this is it with all finished up with the roof and everything. So another thing we've been doing at our office over the last year and a half, we've learned a lot. It's been a long process, but we're trying to figure out where's the sweet spot for your return on your investment for adding extra insulation when you're factoring in the cost of energy and what you're saving. So what we're finding our sweet spot is about a few inches of exterior insulation. A 2x6 wall with Rockwool, a few inches of exterior insulation. We're in our sweet spot. We have a slight increase in the overall construction budget, about 2 to 5%, but we're reducing our energy demand a pretty significant amount. And we're still on, this is a curve of diminishing returns for your increase in budget versus your energy savings. And we're still in the steep part of the curve at that point. As you can see, METHOD.TO does fall outside of this curve. And what, Greg was just talking about this as well, it's because energy in Ontario is so cheap, at this point, you're really paying for your comfort and you're paying for the durability and the longevity of your building. So we did some air testing. I won't go over this much, but we reached about 1 ACH and 0.8 ACH. We think it's much better than this, but the volume of this building is so small, and ACH is directly correlated with the volume, surface area to volume ratio. So this, we think it's better, essentially. We think we're doing good. Russ Richmond actually did the testing, and he thinks we're below the 0.6 in actuality. He did give us another metric, but I didn't want to complicate things today. We also did some thermal imaging. So just a few things I want to point out here. First of all, you can see that the screws, some places where we didn't connect with the studs, and we actually did much better than we thought we would. We didn't miss as much as we thought. But you can see they're colder. They're not significantly colder if you see the temperature gradient here. And we've been through 2 winters and have had no issues. But we could also insulate those. We could foam the screws that don't connect. Hopefully the process will get better. We also had some leakage at the top corner of the roof, and we didn't actually SIGA the roof because we thought the blue skin going over the roof and down to the wall, that connection would be sufficient. But we're regretting that we didn't do that. We think we should have SIGA'd every connection. So that's lessons learned. We then needed a more permanent location to test. You guys know all about this. So Modus Homes, they helped us to move the shed, which was a feat, to the Evergreen Brickworks, where it now lives. So this is us picking it up. This is us dropping it off. And this is now its new home. So it's now with Evergreen Brickworks. We've collaborated with Ryerson University. They're doing some testing on it. A student is doing his master's thesis on it for hydrothermal performance. And he's installed this awesome looking weather station that's going to be testing the kind of the microclimate of where this is located. There's 54 sensors and 2 heat flux sensors in 2 locations, and that's how he's going to be testing the hydrothermal performance. As you can see, the equipment's quite complicated. This has really only been functioning for the last 2 weeks. Unfortunately, I was hoping to have a bit more data at this point. But right now, so the top this is the north heat flux sensor, and this is the south heat flux sensor. And what we're getting is an R value of about R55 and an R value of about R40. And the nominal R value for the wall, because he decided he wanted to introduce some interior bat as well, so it should be R50. So we're above on the north, we're below on the south, and we think the south has to do with the solar radiation because as most insulation products do, they reduce their performance at higher temperatures, but Rockwool performs better at lower temperatures. And as we see, it's above nominal on the north. So we're not too sure about the exact reason for it yet. We need more data to correlate first. Lessons learned, I've talked about most of this, but really we need to plan ahead for testing. We basically had to rip a couple of sections of the shed apart to put the testing equipment in. But we were very careful about it and we put it back as was. And sourcing the screws, hitting the studs, and just general acceptance by builders. We want it to be something that we can learn from the construction industry. They know a lot more, they know everything about construction, and we need to learn what they know. And gain feedback, continue to spread the METHOD.TO word, and we want to facilitate more testing, especially deflection testing, different cladding weights, and greater thicknesses of insulation. So thank you, and thank you to everyone who made this possible for us.